And welcome back. Let's go ahead and move on to pH and titration. They're not the same thing. They're not always seen together, but they frequently are.
So pH is a measure of the concentration of H+ or hydronium ions in solution. And it can measure across a huge range because it is a logarithmic scale. Okay. So logarithms are a sort of the inverse of the exponent. So log base 10 of 10 equals 1. Log of base 10 of 100 equals 2. Log of 1,000, log base 10 of 1,000 equals 3. That is to say 10 to the first, 10 to the second, 10 to the third. Right? So what logarithms tell you are the exponents. So if you have some sort of graph on a normal scale, 1, 2, 3, ... it's going to look something like this if it's exponential. But when you plot it on a logarithmic scale, 10 to the 1, 10 to the 2, 10 to the 3, it'll look straight. Because, every tick you go up on a logarithmic scale is a power of 10. And pH is a logarithmic scale because pH, lowercase p, capital H, is equal to negative log base 10 of the concentration of H+. First off, the lowercase p here basically is telling us negative log of whatever comes afterward. And then the capital H means hydronium ions. The reason it is negative is because the concentration of H+ is usually less than 1 molar. And just log of 0 is negative infinity. Log of 1 is 0. So any number between 0 and 1, the logarithm of that number is going to be a negative number. So because our concentrations are usually between 0 and 1, we just throw a negative number in there. It makes it a positive number, which is a lot easier to deal with. Another advantage, of pH, in addition to turning these numbers positive, the pH turns them from these tiny fractions into a number that's usually between 1 and 10. You may have noticed that you have 10 fingers. We like numbers that are somewhere between 1 and 10. So pH of 3 is going to be a concentration of hydronium equal to 0.001 molar. That's a fairly acidic solution right there, but it's still a fairly small concentration of hydronium. pH of 9 means you're looking at an H+ concentration of 0.1, 2, 3, 4, 5, 6, 7, 8, 9 molar. And that is the other advantage. Not only does it give us a number between 1 and 10, it also lets us deal with these really large ranges of concentration. Okay. So pH of 1 is 0.1. Let's see, pH, concentration, pH of 1. pH of 10 is 0. It's a really big scale, it's a really big distance, and the pH scale makes it a lot easier to work with it. The math is nicely straightforward, negative log of whatever you're dealing with. But of course, you're going to want to be able to go in the other direction. Going from concentration to pH is all well and good. How do you flip it around? How do you solve this for H+? Well, let's go ahead and clear off our paper. pH equals negative log of H+. Well, first, move the negative sign over to the other side. Log of H plus equals negative pH. And then what you do is you take 10 to the power of each side. So 10 to the log versus 10 to the negative pH. So 10 to the log of x equals x. So that means that by doing that, you've got an H plus by itself, and it's equal to 10 to the power of negative pH. So pH equals negative log H plus, and H plus equals 10 to the negative pH. Those are your two equations that will allow you to move back and forth between pH and H plus. One of the things that might confuse you is that even though we're talking about the concentration of H plus, the fact that we're looking at a negative logarithm means that a very low number is what makes it acidic. A very high number makes it a base. Okay? And 7 is neutral. 7 is neutral because of water. Water is what's known as an amphoteric substance. Water is amphoteric, meaning that it can be either a base or an acid, OH minus versus H3O plus. And it is also a self-ionizing substance, meaning that two water molecules can react to produce H3O plus and OH minus. And a perfect solution, a pure solution, I should say, of water is always going to have a little bit of hydronium and a little bit of hydroxide floating around in it at any given time. And that's going to be a concentration of 10 to the negative 7 for each of them. And negative log of 10 to the negative 7 is just 7. So that's why a neutral pH is 7, because water, pure water, is what we decided to make our neutral solution. So 7 is neutral, low is acid, high is base. Now, with concentration and stoichiometry and pH under our belt, let's go back to titration. You'll remember this from one of our labs. We did a very simple titration. Titration is an incredibly powerful and incredibly useful tool in the lab. Titration is when you slowly add a known solution to an unknown solution in order to characterize that solution. It lets you find out some information about that solution. And you can do it with all sorts of solutions. You can do it with all sorts of information. It is incredibly useful. And so we use it a lot. So you're going to see it a lot. So let's start with a very simple thing. If you have 1.2 molar sodium hydroxide and you have 2.3 molar hydrochloric acid, what volume of that sodium hydroxide will neutralize 37.5 milliliters of the hydrochloric acid? Here's our setup. Okay, we have a burette with 1.2 molar sodium hydroxide, and we have a beaker with 37.5 mils of 2.3 molar hydrochloric acid. Now, when you mix an acid and a base, what kind of reaction are we talking about? You should have immediately shouted neutralization reaction at your screen. Okay, so NaOH plus HCl yields NaCl plus H2O. So 1.2 molar, 2.3 molar, 37.5 mils, and question mark. So this is a nice simple reaction. It's a 1-to-1 reaction. 1 mole of sodium hydroxide reacts with 1 mole of hydrochloric acid to produce 1 mole of sodium chloride and 1 mole of water. So all we need to know is how many moles of HCl because that is going to be equal to the number of moles of NaOH. And the number of moles of NaOH, that is because 1 to 1. Stoichiometry. Very straightforward in this case. So how do we get moles of HCl? Well, we have concentration and we have volume. 2.3 moles HCl per liter of HCl times 0.0375 liters of HCl equals 0.086 moles HCl. And 0.086 moles HCl times 1 mole NaOH per mole of HCl, 0.086 moles NaOH. Yes, I didn't really need to do that, multiply by 1, divide by 1, but I wanted to go ahead and spell it out, trying to make it clear. All right, now we have moles of NaOH and we have concentration of NaOH, so we can find volume. Let's go ahead and clear out some room so we can do exactly that. Concentration equals moles over volume. Volume equals moles over concentration. So 0.086 moles of NaOH divided by 1.2 moles per liter. Moles cancel, liters comes up top. It's equal to 0.072 liters, or 72 milliliters. And that is our answer to that particular question. But let's go ahead and double check really quick. Does our answer make sense? Would it take about twice as much sodium hydroxide or twice the volume, I should say, of sodium hydroxide to neutralize that hydrochloric acid? The answer is yes, because the concentration of hydrochloric acid was about twice as much. So the volume of sodium hydroxide is going to have to be twice as much in order to get an equal amount of moles to neutralize it. Well, unfortunately, I neglected to put a concentration on this next bit. I'm going to go ahead and edit this slide right now in order to fix that. So, if 12.5 mils of nitric acid neutralizes 25 mils of 0.750 molar ammonia, what is the concentration of the nitric acid? So first thing you're going to want to do, once again, this is a neutralization reaction. I'm going to go ahead and leave it purple. I like the purple. And the nitric acid plus ammonia is going to produce ammonium nitrate. We need a balanced reaction before we do anything, and this reaction is balanced, so we're done there. Notice it is once again 1 to 1. Nice and simple. Now, we don't know the concentration of nitric acid, but we do know the volume, 12.5 mils. We also know the concentration of ammonia and the volume of ammonia. This is fairly straightforward. MAVA equals MBVB. Because the moles of the acid are equal to the moles of the base, because it's a 1-to-1 relationship. We don't need to do all of that math all the way through. This is fairly straightforward. This is the one we're looking for, so we'll go ahead and rearrange our equation. The concentration of the acid is equal to the concentration of the base. That's the volume of the base. It's B, not a 3, divided by the volume of the acid. 0.750 molar times 25 mils divided by 12.5 mils. Again, so long as you keep the volumes in the same units, they'll cancel out nicely and leave us with 1.50 molar, the concentration of our acid. And finally, our final example for this slide, you mix 10 mils of 1.5 molar potassium hydroxide and 20 mils of perchloric acid. What is the pH of the perchloric acid? I didn't ask for the concentration, I asked for the pH. Once again, we're going to need a balanced reaction. Potassium hydroxide plus perchloric acid reduces potassium perchlorate and water. For this third example, I have once again chosen a nice 1-to-1 relationship, 1-to-1 ratio. That makes it simple. Now we have a 1.5 molar solution of potassium hydroxide and a 10 mil solution, or 10 mils of potassium hydroxide was added to the acid, whose concentration we're trying to find, and we had 20 mils of that acid. So once again, MA equals MBVB over VA. Note, you have to be careful. This particular equation only holds true for a 1-to-1 relationship. If you have a diprotic acid or a triprotic acid or a multi-hydroxide, polyhydroxide base, you're going to need to change things up. And it might be safer just to go through the full rigmarole of doing stoichiometry. For this example, I'm going to not do that. I'm going to save my voice, save my time, and just power through with this. So it's 1.5 molar times 10 mils divided by 20 mils is equal to 0.75 molar. But I didn't ask for the concentration, I asked for the pH. pH is equal to negative log of concentration of H+. Fortunately for all of us, HClO4 is a strong acid. Hopefully you'll remember that in the future. Strong acid, strong base. You don't have to worry about anything else. For a weak acid or a weak base, the pH is going to be a more complex situation. But for this, fairly straightforward. It's just going to be the concentration of the acid. So pH equals negative log of 0.75. And that means that our pH is equal to 0.12. It is a unitless number, and an important thing to remember is that for pH, the only numbers that count for sig figs come after the decimal place. 0.12 has 2 sig figs, 1.12 also, pH of 3.12 or 7.35. These all have 2 significant figures. The numbers to the left of the decimal place do not count towards significant figures for pH. Only the numbers to the right of the decimal place. That's confusing. Deal with it. Okay, so the pH of a 0.75 molar solution of perchloric acid is 0.12. It is a very strong solution. Of course, our base, the potassium hydroxide, was a ridiculously basic solution. It has a pH above 14. It's really, really basic. And that does it for this set of slides.
And for this unit, we are all done. This is all the material that you'll need to know for the third test. When we return, we'll be starting the final unit, and you can really rev up your engines and get ready to hate me to death.